Yes, this is Chapter 8, Section 2-3, and we're going to call this Part B. Chapter 8, 2-3, Part B. We're going to finish up with the other two types of reactions we've not gotten to yet, so that's single replacement and double replacement. And like I said, when we are going through these, you're going to need your packet. The other part of the packet that we have not gone over yet, you got two tables. One of them is your activity series table, and the other is your solubility guidelines. And I will teach you how to use those, or when you need to use them, today. Starting off, single replacement reaction. This is where you've got one element replacing another within a compound. Now they're giving you a couple guidelines. Metals replace metals, or nonmetals replace nonmetals. When it says an element replaces another element, we call that our free element. So in this case, A represents our free element. If A is a metal, it'll replace the metal within BC. If it's a nonmetal, it'll replace the nonmetal within BC. A better way of looking at this, one that works 100% of the time, is your free element, if it is typically a cation, will replace the cation within your compound, or if it is typically an anion, it will replace whatever is the anion within the compound. Now, just by looking at how BC is written, which one has to be the cation? Which one has to be the cation?
C, B.
Cation is always first, and anion is last.
C, cation.
Okay? Anion is last, cation is first. So, in a single replacement reaction, you will have a free element and a compound creates a free element and a compound. Free element and compound create a free element and compound. And in this one, our free element was probably what, based on the example that's given? A cation or anion? Our free element was probably a cation. So A replaced B. B is kicked out as the free element, and now A and C can combine to form a new compound. So we're going to go back and look and see what else is in the PowerPoint. So again, it shows A replacing B. B is kicked out as our new free element on the product side. A and C form a compound. So we were replacing positive charges. A could have been a metal and B could have been metal. Or give me an example of a nonmetal that is typically a cation.
One more time.
Give me an example of a nonmetal that is typically a cation.
Oxygen.
Hydrogen.
Hydrogen. Okay? It's in group 1 with all those other metals. It is typically a cation. In this example, did somebody else over here have a question before I move on? No? Okay. In this example, you've got copper and silver nitrate that are going to be mixing. I don't know how well you can see it, but what they have is that solution that you see is the silver nitrate. It's going to be a clear solution. And they have taken a copper mesh screen and they have dipped it down into the solution of silver nitrate. And you can tell that that is not a copper mesh screen down below the liquid line, correct?
Mm-hmm.
So here's what's happened. Copper, being our free element, has replaced what within silver nitrate? The silver. Okay? Both of them are metals. So it's kicked the silver out as the free element, and it doesn't matter which order you write that in, free element, then compound, or compound, then free element. And now copper and nitrate are going to recombine to make their own compound. So the copper nitrate is in solution, but you can see the silver has actually come out of solution, and it's little globs and crystals of silver that have formed. We're going to talk about, before we get to the next screen, how did we know that reaction would happen? I want you to look at your activity series. Look at your activity series. In the activity series, you are looking for elements that are more active or reactive than what they want to replace. So in the activity series, we need to make sure that our free element is more active than what it's going to replace. Here was the example. We had copper trying to replace silver. The higher up in the activity chart, the more active it is. Is copper higher in the chart than silver? Look on the left side. It is. Copper, it's slightly higher, but copper is higher on the activity series than silver. So when you try to put those two together, copper will replace silver. That will happen. That's how you read the activity series. Notice it says activity of metals, but what is the one non-metal that's in that series? No. Look under your, it's your hydrogen. Okay? Hydrogen is typically a cation. If you look under the other side, it's talking about activity of the halogens or nonmetals. And notice from top to bottom, what is special about this order?
For more active.
They're all diatomic.
Well, no, the order.
I is least active.
The
Electronegativity.
electronegativity, highest to lowest.
Okay? It's the order that you actually see group 17. If you look at group 17 on the periodic table, it is fluorine, chlorine, bromine, iodine. So the activity series is the same way, which makes sense because isn't fluorine our most electronegative element?
Sure. Yeah.
It's our most active halogen. It would make sense that it's going to be first in that chart. So, your products. Again, metals replace metals or cations replace cations, nonmetals with nonmetals. Your free element has to be more active than what it's going to replace. You use the activity series to figure out, will that happen? So in this example, assuming you're not already looking at how it is solved, in this example, what is my free element?
Fe.
What's my free element?
Fe.
Fe. Will it replace copper, sulfur, or oxygen?
Copper.
It's a metal. It's going to replace the metal over here. Now, look at your activity series. Is iron more active than copper?
Yes.
It is. It's higher up in the series. So now you can actually figure out what your products are going to be. This is where the predicting products comes into play. Remember, state standards predict products. So if I gave you Fe plus CuSO4 and said, will this reaction take place through single replacement? If so, predict the products. You're going to look at the activity series and then predict the products. What element will now be my new free element?
Copper.
Copper. So is copper diatomic?
Nope.
Nope. So just write it down. Iron and sulfate now have to combine to form a compound.
So FeSO.
You do the cross charges.
You've got to look at crossing over charges. We're in a small pickle right now because
Fe is a Roman numeral element. But we don't have
Fe has multiple charges. And based on specifically what we're looking at here, you don't know if iron's a +2 or +3 when it needs to form.
Are you going to give it to us like you did yesterday?
I would give you something that would be obvious. So, it's not so much obvious here, so they've went ahead and given you the products, FeSO4. Which version of iron are we dealing with?
+2.
The +2, because sulfate's a -2, and the charges cancel. They cancel, yep. Here's our next one. Again, hopefully you're not looking at it. Bromine plus sodium chloride. What is our free element in this example? Bromine. It wants to replace what within sodium chloride? The Na or the Cl?
Na. It's the cation. So it's
Cl. Neither of them can't because those are two non-metals. It can't replace the new.
Bromine's a non-metal too.
Nonmetals can replace nonmetals.
They don't know which one to replace.
The more electronegative.
One of them's a metal, so it can't replace it.
Okay, which one's the metal?
NA.
Thank you. Sodium's a metal, guys. Has been for forever. Sodium's a metal. What is chlorine? It's a non-metal. Guys, they're both halogens. Y'all should pretty much have those halogens. They should sound familiar at this point. Bromine is typically a non-metal, has a negative charge, so is chlorine. So it wants to replace chlorine and kick it out. Look at your activity series. Is bromine more active than chlorine?
Yes.
Is bromine higher in the chart? No. So even if you put these two together, there will not be a reaction. So I put NR there for no reaction. Put them together, it doesn't matter. You're still going to have bromine liquid and sodium chloride. No reaction. That is single replacement. Single replacement. Remember, can you predict products if it's single replacement? You need to be able to answer that for yourself. Double replacement. For any example that I give you that would be on your test, it will always be 2 ionic compounds creates 2 ionic compounds. I'm trying to make it easier because if I start throwing covalent compounds in there, it can get real hard in a hurry.
You're so sweet.
Yep. So 2 ionic compounds will create 2 ionic compounds for the double replacement reactions that I will give you. If I give you only ionic compounds, real easy. Cations replace cations. Anions replace anions. It's supposed to be super simple. Based on everything that you see here, A, B, and C, D, is A or B the cation?
A is the cation.
Is C or D the cation?
C.
C. C. It's C. Okay? They're showing B and D swapping places. Is that okay? Yeah. Anion's replacing an anion. It's okay. If they tried to replace A with D or B with
What do
C,
you do?
it would be a problem. Because then you could potentially end up with just 2 metals and just 2 nonmetals, and chances are that's not going to be real compounds, the 2 metals. Because we're not looking at alloys. So, cations replace each other or anions replace each other. It doesn't matter which way you look at it if I'm dealing with just ionic compounds. In this example, they show, what's the name of PbNO3?
Lead nitrate. Just kidding.
You got to be more specific.
Lead 2 nitrate.
Lead 2 nitrate. What's the name of K2CrO4?
Potassium chromate.
Potassium chromate. No Roman numerals. So lead 2 nitrate reacts with potassium chromate. And the products are, what's the first name?
Lead chromate.
Lead 2 chromate and potassium nitrate. Let's talk about the reaction you see here, and then we'll get to our other chart. Notice that this first one in this first test tube, that's your lead 2 nitrate, a clear liquid. And the second test tube is your potassium chromate. It's a yellow liquid. When they put the two together, notice what forms. What do you think that's going to be?
A precipitate.
A precipitate. Now, for a double replacement reaction to occur, when you put 2 liquids together, a precipitate has to form. If you do not get a precipitate, you cannot classify it as double replacement for what we're doing. Notice this S right here. That yellow precipitate that you're looking at is the lead 2 chromate that's being formed. That's the lead 2 chromate. If it's a precipitate, it means it is not soluble in water. That means it's not going to dissolve in water. It's not soluble in water. So go look at Table 1 in the packet, your general solubility guidelines. It gives you 6 guidelines. There are many more. These are just 6 common ones. 6 common ones. Okay? Let's look at the potassium nitrate first, because the potassium nitrate that was formed is in aqueous solution, meaning dissolved or soluble in water. Look at rule number 1. It says potassium compounds are soluble in water. Look at rule 2. Nitrates are soluble. So it wouldn't have mattered if we looked at rule 1 or rule 2, that compound was going to be in aqueous state. It is dissolved in solution. Now, for the lead 2 chromate, do you see any rules where lead 2 chromate is mentioned?
No.
And that's correct, you don't. But let's think about it for just a second. I want us to look at some of these other rules and we'll kind of put 2 and 2 together. Look at rule 3. It says most chlorides are soluble except silver chloride, mercury chloride, lead chloride. Silver, mercury, and lead. How might you classify those kind of metals? Silver, mercury, and lead. Especially mercury and lead. It is a term that you've heard before.
Valuable?
Blank metals. No. It's a negative connotation to this. Have you ever heard of heavy metals?
Yes.
Not music. No. Heavy metals. Heavy metals can be something that's very bad. Okay? You've heard of lead poisoning, mercury poisoning, mercury in fish. It has to do with the density of these being heavy metals and not being very reactive. Okay? Rule number none of the other ones are ones I want to talk about. So go back and look at lead 2 chromate. Is lead considered a heavy metal? Is lead considered a heavy metal?
Yes.
Yeah.
Yeah. Okay? It's considered kind of bad, lead-based paints, that kind of stuff. In general, unless you have one of these guidelines that states otherwise, for instance, notice lead nitrate was the first compound. We had a rule for nitrate, right? Rule 2 says nitrates are soluble. If you don't see another rule to state otherwise, if it's a lead-based compound, mercury-based compound, we're just going to assume that it's insoluble. It will not dissolve in water.
But number 3 says is soluble.
It says soluble except. Except. And then they list 3 heavy metals that are not soluble. They're the exception.
So do we want this to be soluble? Or do we
You want one of those compounds you're trying to produce to be considered insoluble
No. Okay.
or not soluble.
So the K and O is soluble, but
It is.
the other one's not.
Correct. Correct. Okay, we're going to end up looking at another example or 2. Okay, again, real easy. Switch your negative ions or switch your positive ions. You're going to get your new products to figure out what is it you're actually making. One product has to be insoluble. That's our precipitate that we're making. Check your solubility table. On this one, similar to what we looked at a while ago, lead 2 nitrate. It's a nitrate. It's soluble with potassium iodide. That's covered in rule number 1. Potassium compounds are soluble. In single replacement, you check your activity series first, then form your products. In double replacement, you form your products, then check your solubility rules. So you go about it just backwards. Do I need to repeat that for anybody?
Wait, say it again.
Single replacement, check the rules, then form your products. In double replacement, form your products, then check your rules.
So what? DR.
In DR, you form your products first, then check your solubility rules. So in this, you have to form your products first. What do y'all want to swap places?
Well, let's see here.
If I pick lead in my first compound, it needs to swap over with what?
Potassium.
potassium. Metal replacing metal. So my first compound would be, let's pick the one, lead will combine with what?
Iodine.
Iodine. Now, lead has what charge in that first compound?
2.
2 plus. So it will carry that 2 plus over to combine with iodine. Iodine has what charge?
1 minus.
1 minus. So when you cross over charges, what's your compound formula?
PBI2.
PBI2. Okay? The next one. Potassium is going to combine with what?
Nitrate.
Nitrate. What's the charge on potassium?
That would be
A 1 plus. What's the charge on nitrate? 1 minus. So the charges cancel. It's KNO3. Now we've already gone over potassium nitrate because that was in the previous example. It is going to be soluble, stay in solution. I'm putting AQ there. Rule 1 says potassium compounds are soluble. Rule 2, nitrate compounds are soluble. There, it's soluble. Now we got to go back and look at lead 2 iodide. Do we have a specific rule that covers lead 2 iodide?
No, but
We do not, but
lead is not soluble.
we will say it's not soluble because it's a heavy metal and we don't have a rule that states otherwise. So that is going to be our precipitate. I put an S for solid. It's our precipitate. Now if I look at the next example, and you'd go back and balance that, the next example is sodium nitrate and potassium iodide. Remember, predict products first, then look at your rules. See if it's going to actually happen. What's my metal in each of these? Because I said I'm only going to give you ionic compounds. What's
Sodium and potassium.
sodium and potassium? So swap those over. Look, I'm dealing with a 1 plus charge and 1 minus charge on everything. Sodium and potassium, both 1 plus. Nitrate, iodide, both 1 minus. So when I predict those, it's potassium nitrate. Well, we've already talked about that. That's aqueous. And sodium iodide. Which rule covers sodium iodide?
None.
Yes, there is a rule.
The first one?
First one, sodium compounds are soluble. So guess what? That one's also aqueous in solution.
In R.
Since there is no precipitate, that doesn't occur, no reaction. So you can put those two liquids together. Those two liquids, their ions are still going to be floating around. It's not going to actually form a precipitate. So no reaction. Use your solubility table for double replacement reactions.